So far we have discussed the solution of Hermite differential equation and Hermite polynomials of order n. Now we are going to discuss today a very important concept, and this is actually regarding the generating function of Hermite polynomial Hn of x. In fact, the function e raised to the power 2tx minus t square, you can see here, this function is actually known as generating function of Hn of x. When you say that the function e raised to the power 2tx minus t square is the generating function of Hn of x, what does it mean? Actually it means we have to show that this function e raised to the power 2tx minus t square may be expressed as summation n 0 to infinity t raised to the power n over n factorial times Hn of x. It means Hn of x can be expressed as the coefficient of t raised to the power n. So first of all we will see the proof of this theorem, and after that we will solve some of the numerical problems based on this concept. So let us start to prove this theorem. How we can prove? Let us see it. You know the exponential function e raised to the power x is defined in this way. This is 1 plus x square over 2 factorial plus x cube over 3 factorial and so on. And in compact form, by the use of sign of summation, we can write this series in this way, that e raised to the power x is equal to summation n from 0 to infinity x raised to the power n over n factorial. You can put the different values of n and then you will see that we simply get this series which defines e raised to the power x. In fact, on the basis of this equation 1, that is the equation which defines e raised to the power x, we can write the expression for e raised to the power 2tx minus t square. On the basis of this equation 1, you can see here. Actually, this e raised to the power 2tx minus t square can be written like this, you know, e raised to the power 2tx times e raised to the power minus t square. Now, when we will use equation 1 to define this exponential function, that is e raised to the power 2tx, you can see we can write this on the basis of this equation 1 in this way. You can easily see this is summation s0 to infinity 2tx raised to the power s over s factorial. Actually in this case, at the place of x there is 2tx and I have taken the number s instead of n. And similarly, e raised to the power minus t square, on the basis of that equation 1, you can write it as summation k 0 to infinity minus t square raised to the power k over k factorial. I have actually used two different indices s and k here. Now you can see this expression may be written as e raised to the power 2tx minus t square equal to summation s0 to infinity and summation k0 to infinity, and for due to this minus sign before t square you should write minus 1 raised to the power k, because this will be just an alternating series, times 2x raised to the power s over k factorial times s factorial into t raised to the power s plus 2k. You can see easily from the above expression. Now let us consider that s plus 2k is equal to n. We consider it. And if you consider that s plus 2k is n, you can see that s will be written as n minus 2k. Now, for a fixed value of k, the coefficient of t raised to the power n from this equation 1, you can easily see when as you can see there is t raised to the power s plus 2k, but we have assumed that s plus 2k is equal to n. So instead of s plus 2k you can write n, and the coefficient of this term t raised to the power n will be what? You can easily see that the coefficient of t raised to the power n will be simply this much, minus 1 raised to the power k, you can see here, times 2x raised to the power s, but you can see s is equal to n minus 2k, so I have written here n minus 2k instead of s, and over k factorial, you can see here, and s is again n minus 2k, so instead of s we have written n minus 2k factorial. So this is the coefficient of t to the power n, which we can easily see from this equation 1. In fact, this should be equation 2 because I have already assumed equation 1 here. So you should write this as equation number 2. This is equation, in fact, 2. And we should write this equation as equation number 3. Now see that limit for s is from 0 to infinity. It means definitely s is greater or equal to 0. So you can see here that now this s is greater or equal to 0. And if s is greater or equal to 0, you can see since s is equal to n minus 2k, so you can write that s greater or equal to 0 implies that n minus 2k, this will be greater or equal to 0. And if n minus 2k is greater or equal to 0, you can see that this n will be greater or equal to 2k. Or in other words, you can say that this k will be less or equal to n by 2. You can see easily. In fact, this result, when you say that k is less or equal to n by 2, actually this gives all values of k for which this equation, you can see here, this equation 3, this equation 3 will hold. So you can write that it actually gives all values of k, for which equation number 3 is the coefficient of t raised to the power n. Now you can see if n is even, then k will be simply less or equal to n. So there will be actually two cases. So see here, if n is even, then k will be less or equal to n by 2, because you know k has only integral value, and if n is an even number and you will divide it by 2, you will get simply in fact integers or whole numbers. But if k is not an even number but it is an odd number, then k will be not less or equal to n by 2, but that will be less or equal to n minus 1 over 2, because n minus 1 then will become even, and then k will have integral values. So you can see if n is odd, then for integral value of k, definitely k should be less or equal to n minus 1 over 2, because you know if n is odd, then n minus 1 will be even, and when you will divide that even number by 2, you will get the integral value of k, because k is integer. K is integer. So to get k as an integer, it is necessary that if n is even, then k should be less or equal to n by 2, and if n is odd, then for integral value of k, this k should be less or equal to n minus 1 by 2. So now we can combine these two conditions. When k varies from 0 to capital N, where capital N will be actually n by 2 and n minus 1 by 2, when n will be even or odd. So combining these two results, we may say that k varies from 0 to capital N, where what is this capital N? This capital N will be equal to n by 2 if n is even, and this will be equal to n minus 1 by 2 if n is odd. So you can write this. I hope you have understand this idea. And now we can write the total coefficient of t to the power n in the expansion of the generating function, that is e raised to the power 2tx minus t square, in this way. So you can see, hence the total coefficient of t raised to the power n in the expansion of e raised to the power 2tx minus t square is given as, in fact, what will be this? This will be summation n0 to capital N. You can see the definition of capital N, just you have seen just now it. Here capital N has been defined. So now we can write the total coefficient of t raised to the power n in the expansion of this function e raised to the power 2tx minus t square, in this way. So this will be my summation n0 to capital N minus 1 raised to the power k 1 over k factorial times n minus 2k factorial and 2x raised to the power n minus 2k. Actually, you can see I have written this expression on the basis of this result. You have already seen that the coefficient of t to the power n is this much, and in that equation I have written the total coefficient of t to the power n. So in this case we take the summation from n equal to 0 to capital N, where capital N has been defined just now. You can see this capital N is n over 2, that is a small n over 2 when a small n is even, and this is a small n minus 1 over 2 when a small n is odd. So this is the total coefficient. Now let us write in this particular manner this expression. If you divide this expression by n factorial and also multiply this expression by n factorial, the result will remain same, you know. So I can write 1 over n factorial times summation n 0 to infinity minus 1 raised to the power k times n factorial. So you can see I have divided by n factorial here and also multiplied by n factorial, so the result will remain same. And other factors are at it, so you can write k factorial times n minus 2k factorial times 2x raised to the power n minus 2k. But you know this expression summation n 0 to here will be capital N, not infinity. So this is capital N. And you know this expression which I have underlined here, this is just the Hermite polynomial of order n, and we denote it by the symbol Hn of x. So you can see this is simply 1 over n factorial Hn of x. Hn of x. So we can now write that the function e raised to the power 2tx minus t square, this will be equal to summation n 0 to infinity t raised to the power n over n factorial times Hn of x. And you can see this is the result which was to prove. So this is all about the generating function of Hermite polynomial of order n. In fact, in next lecture we will see an alternative expression for Hermite polynomial, and then we will solve some of the numerical problems.